Hello, in this video we're going to look at the continuous probability distributions and an introduction to the normal distribution. We will also look at the standard normal distribution table to try and figure out the area under the curve for a given z-score interval. So if we look at the picture on the screen, this is a discrete random variable. Remember, a discrete random variable can only assume a finite or countable numbers with a gap between the values. So if we use the probability histogram for this discrete variable, and this variable can be whatever variable we want it to be, but the vertical axis is the probability. If we look at this example, we can determine the probability of getting a 2. In this case, it's about 0.31. So we can write this as the probability of 2 is equal to 0.31. Now we're going to build into this idea of the area underneath the curve. So let's first look at the width of each of these rectangles. If this is from 0 to 1, and 1 to 2, and 2 to 3, the width of each of these rectangles is 1. So therefore the area for the rectangle that is 2 is the width, or the base, times the height, which would be 1 times the height of 0.31, which would just be 0.31. So from here we can start looking at other examples like how do we get the probability of a 2 or a 3? Well, if 2 is 0.31 and 3 is about 0.14, let me just color code this nicely. Probability of 2 is 0.31. The probability of 3 is about 0.14. So the probability of 2 or 3 will be about 0.45 because we're adding them together. So the areas of each of these rectangles will also be 0.31 and 0.14. So the areas of the two of them together will be about 0.45. Because again, what we're trying to build here is that there is a relationship between the area and the probability for each of these random variables x. So if we were to add up all of these probabilities together, 0.17 plus 0.36 plus 0.31 plus 0.14 plus about 0.02, 0.03, the sum of all of these rectangles should be 1, which is the same thing as the probability. The sum of all the probabilities for a discrete random variable would be 1 as well. So the relationship that I'm trying to build here is that area in probability are the same thing. The area under the curve, or under the picture, or under the graph, is equal to the probability for any given region. All right, so this is for a discrete probability. We can come up with the same type of ideas here for a continuous probability. Remember that a continuous random variable can take on any numerical value or an uncountable number of possible values between any two values. These values generally result from some type of measurement. The graph of a continuous probability distribution is a curve. Probability is represented by area under the curve. Here's the important point that we're trying to come up with. The probability is represented by area under the curve. And the curve is called the probability density function. The area under the curve is given by a different function called the cumulative distribution function, or CDF. The cumulative distribution function is used to evaluate probability as area. So if we look at these two pictures below, they represent two continuous probability distributions, and we're trying to show that the probability underneath the curve for any regions is equal to the area under the curve for any regions. So the left side shows that the total sum of the probabilities is going to be equal to 1, and the shaded area between A and B will represent the probability that our x value will be between A and B. So this is a nice graph that shows a continuous probability distribution, but it's very challenging to try and find the area underneath this curved figure here, especially in graph B. We would need to use some integral calculus, and we would need to know what the function's equation is so that we can actually use integral calculus to find the area under the curve between those two boundaries. However, the special case of the continuous probability distribution that we're going to be focusing on in this particular video is the normal distribution. The normal distribution is a continuous distribution, which is the most important of all the distributions. It is widely used and even more widely abused. Its graph is bell-shaped. You can see the bell curve in almost all disciplines. Some of these include psychology, business, economics, the sciences, nursing, and of course, mathematics. Some of your instructors may use the normal curve or the normal distribution to help determine your grade. Most IQ scores are normally distributed. Often real estate prices fit a normal distribution. The normal distribution is extremely important, but it cannot be applied to everything in the real world. The normal distribution has two parameters. There are two numerical descriptive measures, the mean, mu, and the standard deviation, sigma. If x is a quantity to be measured that has a normal distribution with mean, mu, and standard deviation, sigma, we designate this by writing the normal distribution of mu, comma, sigma. Probability density functions are normally distributed, and they may also be referred to as bell-shaped curves. Here's some important stuff that you guys should take down. If you ever see the phrases bell-shaped curves, normally distributed, or even approximately normally distributed, a normal curve, a symmetric distribution, you should automatically think about using the normal distribution. Now we have from this textbook, this online textbook, which I've given you the link for here, we have a number of different graphs. Each of these graphs represents the same data values. It doesn't really matter what those data values are, but basically the general idea here is as we take larger and larger sets of data values with smaller and smaller intervals or more and more precise values, you'll see that our graphs will approach the normal distribution. And there's, again, the symbols for how to talk about the normal distribution. You'll never need to worry about them. It's what is given in the textbook, so I figured I would show you here, but we have the bell-shaped curve as well. The function itself for the normal distribution is this function down here. You do not need to memorize this. You do not need to worry about it, but basically what's happening in the back end of any of the technology we're going to be using is integral calculus is being applied to that function. All right, so important properties of the normal distribution. Any graph that has these properties can be approximated by the normal distribution. The first thing is that the normal curve is bell-shaped and has a single peak located at its center. The mean, the median, and the mode all have the same numerical value and are located at the center of the distribution. Because the mean, the median, and the mode all have the same value, the graph is symmetric about the mean. The data values in the normal distribution are clustered about the mean. In theory, the normal curve extends infinitely in both directions, always getting closer to the horizontal axis but never touching it. As the normal curve extends out away from the mean and gets closer to the horizontal axis, the area in the tails of the normal curve is getting closer to zero. The greatest concentration of scores are clustered around the center. Relating this to the probability, the likelihood of an event occurring is greatest if the value is close to the mean, median, and mode. And lastly, the total area under the curve is 1, which it can also be interpreted as the probability. As we were talking about before, the area under the curve is the same as the probability for the given region. Thus, the area under the normal curve represents 100% of all the data values. When we say that a distribution of a continuous variable is approximately normal, we are indicating that this variable can be modeled by a normal distribution. However, there are many of these distributions with different heights and widths based on the variance and values of x. If you remember back from the empirical rule, there is approximately a certain proportion of the scores within a range of standard deviations from the mean. This proportion will be the same for any specific standard deviation, no matter which normal distribution we have. Let's look at how the normal distribution can be applied to different values. If we let the mean IQ score for a sample be 100 and the standard deviation be 10, we see this graph. However, the mean and standard deviation can change, and we will still have the same area. Notice that this area is approximately 34% based on our empirical rule. Empirical rule says between the mean, well, I guess this is technically a sample, between the mean and one standard deviation above the mean, we have approximately 34% of the data values. If we click on the link here, we will see this area and this region. Again, this is for a mean of 100 and a standard deviation of 10. We are shading in the area that is from the mean to 1 standard deviation above the mean. However, these values, these probabilities can be applied to any graph regardless of what the mean value is. If the mean value is 75 and the standard deviation is 2, the graph is going to be differently viewed, but the area is still going to remain the same. Now, if I were to adjust the window, give me a second. If I were to adjust the window a little bit, I think I need to, it's not working the way I wanted it to. We could change this so that the graph will look the same. Give me a second, let me just do this. Settings, we want to change the maximum of the y value to, let's say, 0.12. Make this a little bit smaller. Oops, I went the wrong way. Let's make this bigger. Let's make this 4.2. Now it looks almost the same as what the other graph did. And I can manipulate this a little bit more, but the graph will look almost the same because all of the characteristics or properties of the normal distribution are still being met. So we can change this mean to be any value we want to. We can change the standard deviation to be any value we want to. And regardless of the shape of the graph, if we are looking between the mean and 1 standard deviation above the mean, we will always get the same area. And we're using that from the normal distribution. So since the proportion of values underneath the curve, again, basically the empirical rule, can be applied to any normal distribution for any amount of standard deviations as long as the variable is approximately normal. Since each different value of mu and sigma, or mean and standard deviation, can produce a different normal distribution, we say that there is a family of normal curves. And that's what this visualization that I was just trying to use was showing, was that there can be an infinite number of normal curves, each with a different mean and a different standard deviation, depending on your examples. Since we can apply this general picture to any continuous variable, we are going to look at only the standard normal distribution for this video. The standard normal distribution is when we allow the mean to be 0 and the standard deviation to be 1. The standard normal distribution is a normal distribution of standardized values called z-scores. A z-score is measured in units of the standard deviation. Recall that z-scores represent the number of standard deviations above or below the mean. By generalizing any normal curve to have a mean of 0 and a standard deviation of 1, we can easily find where our data values lie within the normal distribution. We can use the standard normal distribution for any normally distributed continuous variable by converting any and all x values into their z-scores. And I've given you the z-score formula that we've covered in previous lessons. The z-score of a data set, a z-score of a data value, x, is x minus mu over sigma, or as I've said in past lessons, the score minus the mean divided by the standard deviation. So again, we're taking any value we want to. It can be some really large value or some really small value. It could be a positive value or a negative value. And if we apply the z-score to it, we can talk about the location of that value above or below the mean in terms of the number of standard deviations. All right, so let's do one example. This example 6.1 asks us to find the area of the shaded region. Remember that the area under the curve is equal to the probability of that interval. So this question could ask something like, what is the probability that from a given sample that our x values lie to the left of negative 0.53 or are less than negative 0.53? There are other videos in my feed and on Brightspace that will show you how to calculate these areas under the normal curve using different types of technology. For right now, we're just going to look at the standard normal distribution tables. The standard normal distribution tables are based off of any and all z-scores from -3 to +3. On the left side of the table, you'll see that there are negative z-scores. On the right side of the table, you'll see that there are positive z-scores. I'm only going to do this for this one example. But basically what we will do here is we will look in the standard normal distribution table to find the area to the left of the given z-score. The given z-score is -0.53. So we can look in our table here on the left side, look for -0.5. We are looking at this row here. And then we are going to find the column that has 3 in the hundredths place value. And this table shows that the area to the left of the given z-score is 0.2981. All right, thanks for watching. Be sure to check out the other videos that show how to do these with technology.